So today's lecture really is focused on energy sources. Where do we get our energy? We've talked about combustion sources, fossil fuels, and so on. This is really comparing all of them, including electrical sources, and really focusing on electricity generation. So we have different sources, and of course, oxidation and reduction, redox chemistry, those would be the sources for the batteries and things like that. But honestly, that's what our combustion is too. It's a redox reaction. It's a reaction with oxygen in the atmosphere. We don't typically think of it that way. We just think of it more as combustion. And then there's electromagnetism, and then photovoltaics. We get into material science. So we have all kinds of things in here that are cross-disciplinary. And then we'll talk about storage, how we store the electricity. And this is really an area that, as you know, it's like constantly improving and changing. Think about all the battery technology. So how we store that energy. There's short-term versus long-term storage. So not everything is stored in terms of batteries. We've got some long-term storage, like pumped hydro or compressed air storage. And so we can store things in interesting ways. And then there's this idea of impedance. So, a lot of our little batteries that we're used to, they don't give you a lot of watts. They might have a decent amount of energy stored into them, but how fast the energy comes out. That's sort of the resistance of the source. And so the source is not a resistor, so we don't use the word resistance, but how hard can you pull the electrons out? And that resistance-like behavior is called impedance. So how fast can we get the energy back out of the storage medium is impedance. So you have high impedance and low impedance. And that's why we still use lead-acid batteries in cars, because the lead-acid battery has a really low impedance. It'll deliver, if you look on the top of the battery, 300, 500, 700 cranking amps. Like it'll dump out 600 amps, and that'll help you turn the motor. You have an electric motor that turns the engine around. That's your starter. So you do have an electric motor in your vehicle. It's called the starter. And the battery turns that starter motor, and that starter turns the combustion engine that starts the compression and the explosions and power stroke and all of that. And then once your motor starts taking over, then the starter quits. So that's what's going on. But we need that low impedance lead acid battery. We just would like to get rid of the lead. It's heavy, it's toxic, and so on. They're starting to make lithium ion batteries, which have low impedance for your cars, but they're like $1,000. They're 2 or 3 times the cost of a lead acid battery. And then there's lossless or lossy storage. So we want, if we store electricity in a storage medium like a battery, we don't want it leaking out. And batteries do leak. Okay. And so this is our energy conversion chart here. And we'll work with this chart quite a bit today. So looking at all of these different forms of energy, hopefully you recognize all of these. So this is just the different forms that energy takes. And really, this whole planet has been operating on solar power. Okay, so the sun has allowed, with photosynthesis, all of the vegetation 65 million years ago to grow and get compressed into peat and then form coal. And so we'll talk about that somewhat today. But that was way in the past. Now we have that as chemical fuel. So that light was turned into chemical fuel using photosynthesis. We still do that today with biofuels, but notice how inefficient photosynthesis is. It's just not a rapid way to generate chemical fuel. But the sun gives us 5 million exajoules per year. So because the sun is so bright and you can distribute that energy across all the different plants, you can generate a fair amount of chemical fuel. We have nuclear power, and then we also have gravity. So our waterways that go downhill, we can use that, and compressed gases. We even also have thermal, the compression or expansion of steam. So geothermal fits into this one too. We burn the fuel, either chemical or nuclear, to make heat, and a lot of times that heat is in the form of steam. And so the energy is now in the steam. It's not doing anything yet, and we can spin a turbine and turn it into mechanical energy. Then we put an electric generator on the mechanical energy spinning thing, and we get electricity. But there's other little strange ones, like batteries go straight from chemical to electrical. And so fuel cells and batteries, the only difference of fuel cells and batteries are whether the fuel is enclosed or not. So like a battery, if you'll notice, a battery is in a nice little package, and you can't add any more reactant. That'd be kind of cool if you could. Like you have a battery and you keep adding in your reactant. Well, that's what a fuel cell is. So it's a battery where you can add in more reactant or regenerate the reactant externally to the battery. So we could go straight from chemical to electrical with fuel cells and batteries, and then we could store energy. If we take electricity and we break apart some molecule, the simplest to think of is water. So if we take water and break it into hydrogen and oxygen, that's called electrolysis. Okay. And so now you have chemical fuel again. You have hydrogen and oxygen. And if you run those through a fuel cell, a hydrogen oxygen fuel cell, you get back to electricity. So we can go back and forth with those. Electrolysis is pretty efficient, but the fuel cell technology is less efficient. And so that storage medium would be lossy. We would lose some electricity by storing it that way. This one is interesting, hot water heater and thermocouple. So we can use electricity to heat water, very efficient to do that. But then getting back to electricity, just using that heat, thermocouples are only 7% efficient. So what is a thermocouple? Well, two dissimilar metals, when they're in contact with each other, they produce a voltage, and it's temperature dependent. So you can raise some of these metals up, and you can produce a small voltage. And so you can turn thermal energy directly into electricity using these metal junctions. So that's what a thermocouple is. So these are all our different efficiencies, and we can use this diagram to kind of understand how we convert from one to another. So here's our energy flow in the United States. This was in 2002, and our primary use of energy, this was in a previous lecture as well, 115 exajoules per year. I found the updated chart. So this was the 2019. And so we went down a little bit. I don't know either we got more efficient or what, but from 2002 to 2019, we went from 115 exajoules per year to around 101. And so, so that's 2019. Now, what happened in 2020? Does everybody remember? You guys ought to know. Yeah, COVID, and we shut down the economy, but not completely. We still had remote work and all of that. And we only went from 100 down to 92. So we only lost really 93. Only lost 7% of our energy consumption, and shutting us down that much. That's just unbelievable to me that much of a disruption only accounted for like a 7% savings in energy. And this is one of the reasons why I say there's no economic way to address climate change by reducing what we use. Because, I mean, we're not going to be able to live if we shut down, 10 times more than we shut down for COVID. I'm just saying that's something you need to keep in mind. It's not like we can just make small changes to our lifestyle and we're going to address our energy usage. We need to change how we generate energy. We're not going to be able to conserve our way out of this, is my point. Okay. Now, also, this shows that our electrical generation is around 35%. And so that's, and the USA is about 33% overall in terms of our energy usage. So what that means is what we consume, we bring in 100 exajoules per year, we get about 33 exajoules in useful energy out of it. Now, a lot of that is lost to this problem with load on the electrical grid. So this is something that's really important for our society, for the world in general. And so what we've done for our country in particular to help our efficiency is we have this base electrical generation. So right here, we will always need this amount. Okay. And so that's our base load. And we can run that on slow systems that produce an enormous amount of power, but are slow to start up and slow to shut down. So it takes a long time to bring up and shut down a nuclear power plant or a coal-fired power plant. But natural gas turbines, those can be turned on in a few minutes. Okay, and so what we do is we can run these natural gas turbines to level out the load. And so what we see during the day is like from midnight to 6 a.m. there's a drop in demand. And so we can turn off that natural gas turbine, and then around 8 a.m. when people are getting to work, then air conditioners come on, lights come on, all kinds of activity happens in the house. People are blow drying their hair, they're cooking breakfast or whatever. Then there's a huge demand spike every morning. And we can have natural gas turbines that run both of these as well to level things out, because those can be turned on and turned off. So that's what we've done in the United States. And also that means we've wasted less coal. And so we have actually reduced our CO2 emissions in the past decade by doing this. We built a lot of natural gas turbines. And so we backed off on our coal-fired power plants, which produce more CO2, and use more of our natural gas reserves, which produce less CO2. And yet we haven't changed the amount of electricity that we generate, really. So it's been a very successful program. Now, if we were to switch our coal over to nuclear, we'd use even less fossil fuels and produce even less CO2. So here's our typical customer. This is Entergy Texas, which is the power company that I use here in Huntsville. And so this is amount, like if you wanted to take the average power, monthly usage, 1,000 kilowatt hours, what's the average power in terms of watts? It's only about 1.3 kilowatts. So if you were to look at a generator, like if I'm going to Harbor Freight and I need to buy a generator, what could I run my house on? Okay, the average is 1.3 or 1,300 watts. That's a pretty cheap generator, 1,300 watts. That's probably a $200 generator. I could run the average power of my house on for $200. Now I have to supply the gasoline, but still. Now, if I wanted to do peak power, so if you have on the side of your house, like I have a 100 amp main breaker box. So my house is sort of capped at 100 amps. But if I ran 100 amps at 120 volts, that's 12,000 watts. Now that's a more industrial size, maybe diesel powered generator, but still you can have those installed for your whole house. And we see a lot of those in our neighborhood because in the woods, we lose power a lot. The trees hit the power lines, short things out, power goes out, and then you hear the generators kick on. And so if you want to know what the minimum power is in your house, then turn off your fridge, your water heater, your air conditioner, all of those things, and wait an hour or so, and then go and look at the meter and see how slow it's turning, because there's still little things on in the house that you don't know about, but that would be the minimum power that you would have going. So let's talk about our storage, energy storage. So we have sort of what I say about whole grid leveling, where we can keep the whole grid stable. One of the ways is really cool. It's called pumped hydro. And so you think about hydroelectric. Well, not every area has streams that are or rivers that are conducive to hydroelectric dams and so on. But they can still, if they've got mountains, they can build reservoirs up in the top of a hill here, and then they pump the water up that hill. And you say, well, that uses electricity. Why would you pump water uphill? It's a storage medium. So when would you do this? Midnight to 6. Okay, so from midnight to 6, the demand goes down, and you could just use that excess electricity to pump water uphill. And then at 6 a.m., you turn it around and generate electricity with that water that you pumped uphill. And then you store that low demand, and then you pull it out during high demand. And this is the easy way to store electricity. It's pretty cool. And all you're running is electric pumps, and those are very efficient. So we pump water uphill at midnight to 6, and then let it come downhill from 6 a.m. to noon, and then we're in really great shape. Okay. Now that would be slow or high impedance, right? It's you're not going to be able to pull all that water through your pumps right away. I mean, it's gonna be a certain rate that you can pull down. These are really fast, low impedance energy storage, and this is a flywheel storage. So inside this little vacuum chamber, you've got a really heavy object on an electric motor, And so you can spin it up and get it going, and it's mechanical energy. And then later, when you want to pull that mechanical energy out, you clutch into the generator, and then it slows down and generates electricity. So this would be a great way if you had a scientific instrument. And that's why you see this one with NASA here. You got scientific instruments that demand a lot of electricity, and then don't demand it or whatever. Up these swings, this kind of mechanical storage can level out those swings, or maybe the power goes off in your building and you still need a lot of current to get your instrument to shut down or get it through the gap. We have these kinds of storage media. You could also do this in whole buildings. So you could have the basement of your building filled with these kinds of centrifugal energy storage, so that your building pulls the electricity midnight to 6 and stores it in these mechanical energy storage. And then at 6 a.m. when the power comes up and the AC and everything starts kicking in, you draw from your own sort of mechanical batteries. So this is like a mechanical battery, not a chemical battery. So you're just storing electricity in mechanical motion. And you see that's pretty efficient. You can get 60 to 90% of that electricity stored in the mechanical energy. And then when it's time to pull off of that mechanical energy, you can get it back at 98% efficient. So here's our flow, or our storage spectrum. Down here, these storage times in, tenths, hundredths, or thousandths of a second, that would be like those mechanical energy storage or capacitors. But then up here at the 10-hour range, and megawatts, hundreds of megawatts, that would be commodity storage. That would be like that pumped hydro. So you just have a spectrum of all these different ways that you can store energy. Let's look at these flow batteries. So it's a battery, but it's a fuel cell. You can flow the chemicals in and out. You can refresh them, you can resupply them, and so on. And this one is a polysulfide bromide cell. And I'm really just kind of going through these just to show you all of the varieties of batteries that we have. Not all batteries have just, these little encased, metals reacting with each other. Some of these are nonmetals, like these bromide cells. Okay, reacting with sodium. And so there's already some large facilities. Like here's a 15 megawatt facility using these. Here's the storage tanks for the materials. And so why would they be building these? Well, they build these next to solar and wind farms. So when the sun's not shining, you pull off the battery. When the sun's shining, you store up the battery. Same with the wind. When the wind's blowing, you charge up these flow cells, and when the wind stops blowing, you discharge them. Well, here's a vanadium one. This one's kind of interesting. On the negative and positive half cells, we've got all of these different oxidation states for vanadium, which I think is really an interesting cell. So this vanadium fuel cell uses the vanadium 2 and 3 state and the 4 and 5 states. They're in mild sulfuric acid. And so there's been some commercial use of these. But the battery can be as high as 85%. So that's great. You store 100 joules, you get 85 back. Okay. Here's a zinc bromide fuel cell. This one has been somewhat miniaturized. What's miniaturized? Well, this is like a semi tractor trailer box, those big containers. And so you can drop this in. The military can bring it in a helicopter, drop it down, and now that whole installation has battery power and can run all of their equipment. And not only that, but it's a storage medium. So if they do get up another a way to generate electricity, they can charge this thing up, and then they can use it when the electricity turns off. Again, 75% efficient, so not bad. Here's lead acid storage. So this is a huge facility here in Chino, California. So a 10 megawatt facility filled with lead acid batteries. So look at all of them in these racks. That's pretty, what do you want to say? Low tech, if you will. Now I'm sure there's a lot of electricity, like monitoring electronics and so on, but it's pretty much just setting up the lead acid batteries end to end and putting them, in clusters to give you the voltage that you want. Okay. And then this one I call the hell and brimstone, or fire and brimstone battery, because it has molten sulfur and molten sodium. Yeah, which brimstone is sulfur. So this thing, you know, this is set up to supply electricity if the wind drops off at this solar wind or at this wind farm in Japan. But it's a 51 megawatt battery set for this wind farm. Each one of those little cells is a 2 megawatt cell, so that's pretty huge. About 89% efficient, so that is beautiful. You can, I mean, that's the highest one we've seen so far. But absolutely, you would not want this thing to leak. Like if air got in there, sulfur could catch fire, the sodium could catch fire, water is going to react with the sodium and produce hydrogen gas. This is not good in terms of safety, but you know, it's being implemented. Kind of makes me nervous. And then there's lithium-ion batteries, which we use. These are lightweight and have a huge efficiency. Some have reported 100% efficiency, so that's hard to believe. You're going to have some losses, but this is the most efficient so far. So that's why we use lithium-ion batteries for our laptops and all of these different things, because it's great. You can charge it up, long life, 3,000 cycles at 80% depth of discharge, and that's improving year on year. And then we have metal air batteries, similar kind of thing. These are fairly cheap. This is like a potassium hydroxide electrolyte. So, and then supercapacitors. So this is for the fastest discharge. A capacitor can generate almost all of its current instantly. So you have it charged up, it's ready to go. It also is what makes them dangerous. So some of the capacitors can hold a lethal charge. So if you get across the electrodes, it can kill you before you even know. We had did I tell y'all when we talked about lasers in PChem 1 about the power supply we had? There was a power supply that we had to have these capacitors that were about the size of a half-gallon milk jug. And so they could there were 6 of them, and they all contained a lethal charge. And so you couldn't work in that cabinet. Even if you unplugged it from the wall, those capacitors were still charged up. So you go fiddling around in there, you could kill yourself and not know it. So, you know, when it says high voltage, no entry and all that, I mean, those signs are for real, because you could unplug it from the wall and it could still have enough electricity in the capacitors to kill you. So the very first thing you did, if you had to go in there and do any maintenance inside this cabinet, was to ground out the capacitors. And that was always the job of the new person in the lab. Because you had this long screwdriver, big metal screwdriver, the end was all chewed off, you know, and it was because you reached in there and you grounded out those capacitors, and it was really like a shotgun blast. It was loud, big flash, boom, you know. Everybody always had a bump on the back of their head because you reach in there and bam. But it was exciting. After you did it once, you wanted to do it again. But we always let the new person come in and, you know, do the grounding. So that was great. So this is great for automobiles when they want to accelerate. So you have a battery for storage, and then you have capacitors that charge up with the brakes. You know, you hit the brakes, it charges up those capacitors, and you're ready to accelerate again. And so you can actually, I mean, they've done drag races. The electric cars can out-drag any combustion engine because of these ultra capacitors, dumping tons of current through the motors, especially 4-motor vehicles. When you got a motor on each wheel, those things accelerate like crazy. There's such low friction, and we can dump a ton of current through those electric motors. Now for really, really long-term storage, the opposite end of the spectrum. We talked about pumping water uphill. You could also just pump air into a tank. But think about how big your tanks can be. I mean, they're somewhat limited in size. Surprisingly, a lot of our tanks are limited in size just because we have to transport them around the country, and roads are only so big. I mean, you've been on 45 when you've seen these big tanks, right, coming down with the trucks that have 25 wheels or whatever. But even then, it's still limited to the bridges. It's limited to the size of the road. And so the storage tank would be a problem. So what do? They use caverns. So you don't have to build the tank. You just have a place that's on top of a salt dome cavern, and then you plumb it in, and you start pumping air down into the cavern and pressurize the cavern. And then when you want to pull on that, you just use that air to come out and spin your turbine and generate electricity. So this is compressed air storage. So it's pretty good. So this is and we're an order of magnitude higher than the flow cell batteries. We're at now hundreds of megawatts. So 290 megawatt unit in Germany. The largest ever is planned for construction in Ohio at 2,700 megawatts. So these are fantastic. It'll compress air to 1,500 psi in an existing limestone mine, about 2,000 feet under the ground. And then we have pumped hydro. Here's a beautiful aerial shot of that. And you see the normal hydroelectric dam only has this elevation of a drop, right? But look up here. I mean, there's let's just see how many times that is. So 1, 2, 3, 4, what do you say? 5 times the height. And so you got 5 times the pressure, all things being equal, to generate that electricity. Now it says worldwide, there's 90 billion watts of pumped storage, so 90,000 megawatts. Yeah, and then we have the flywheel storage, which I've already talked about. So, but again, some of these are 90% efficient, so that's fantastic. So here's all of the different storage media that I've talked about, and whether it's like an energy application or a power application. So remember, energy is joules, and it might be low wattage, so we can pump the storage up the hill or compressed air, and that's going to give you energy for a long time, but it's high impedance. It's hard to pull that energy out. Whereas the capacitors, those are more high power. You can't store a lot of joules in a capacitor, but whatever you store in there can come out extremely fast, and so that would be a high power situation. So there's always a balance between whether it's a high energy or high power storage medium. Now let's talk about alternative generating capacities. So here's one. It's a steam power plant, but using solar energy to heat the steam. So we run water through these little tubes. Down here in this little reflectors, so if I'm going to expand on that, it's got a parabolic reflector like this and a little glass or quartz pipe. And so the sunlight comes and reflects and hits that pipe and heats it up. And so it generates steam, and after it's at steam, it's still being heated, so it'll generate superheated steam that'll go through and spin a turbine. So that's pretty neat. But the interesting thing is this goes over 1,600 acres, and it generates 354 megawatts of capacity, so 354 megawatts. Now, I compare that, if you look at this road right here, so this road right here, single lane road, it's about the same width as like these roads right here, maybe over here too. And so I tried to get the same footprint, the same picture scale. And these are my wife's from LaGrange, so I always use their power plant as an example. They've got 3 power generating stations. It's a coal-fired power plant. This black part right here is the coal field. The trains come in and dump their coal there, and then they pulverize it and bring it into the coal-fired power plant. And they have 3 of these at about 600 megawatts and one at 450. So anyway, you look at the footprint of this solar area, and it's generating 354 megawatts. And then the footprint of 3 coal-fired power plants is much smaller. Let's look at photovoltaic cells. So this is an interesting phenomenon. Light comes in, hits this diode area, and it promotes a photoelectron. And so now you have this photoelectron up here, and it can't go back. So this path is blocked. It has to go through the circuit to get back to the other side. And so that's all photovoltaics is doing. It's charge separation. So light comes in, separates the charges, and then the electrons have to go through your circuit. So here's a solar park in Germany, 40 megawatts. So that is an enormous solar park. If you look at the road size here, I mean, that is absolutely amazing. But again, you could compare that to the Fayette Power Station here. Again, a similar kind of road scale at 40 megawatts versus, all three of these. So how many, this generates 41 times the power of that solar park. So, it's footprint wise, and not only that, but the farther you transport the electricity, the more you lose in the power lines. And so the solar park has to be fairly close to the populated area where property values are extremely high. Now, the coal's small generating footprint. This is the generating footprint. What about the mining footprint? So I wanted to take a little side trip today and add a couple of videos on the footprint of coal. So this is the footprint for the power plant, which is not that bad at all. I mean, we're generating, this many megawatts compared to the footprint of solar. But let's look at the coal mining footprint. So this is a coal mine, and this is how they get coal out of the ground. So anyway, I like explosions too, so that's pretty cool. So what they do is they drill a network of holes, and then I think this is all just explosions. Oh, here it goes. This is beautiful. So they drill a network of holes, and then they take ammonium nitrate fuel oil and they pour it into that deal, and then they run detonation caps down in there, all connected by primer cord. And so they have one detonator on the primer cord, and it runs through and detonates all of those little holes. The idea is to just crush the rock and loosen it up so that you can scoop it up with your bulldozers. Obviously, this is a remote area, but it's still a huge footprint, right? Okay, so we got a whole bunch of those. There's 5 minutes of explosions. You guys can go check it out. That's great. Now, you may look at that and you go, wow, what an environmentally disastrous thing, right? We're just like chopping the tops off of mountains and so on. And so this is a longer video, but I think it's worth watching because it's really interesting to see. For one, they didn't have any regulations on strip mining before the 70s. And so they would come and strip out the coal and then just leave this big pit of overburdened rock and then exposed minerals too. And so this is in Ohio, in Iowa, the southern Iowa, where there was a lot of coal, before the 70s. They have now these open mines that are just a mess, and they're trying to reclaim them. And now, since the 70s, we have regulations that the coal company has to pay into a bonded trust that will hold the money for the reclamation activities. So they come in, they put a lot of money up front in this bonded account. They extract the minerals, and then they use that money to replant the topsoil, reseed the grass, and plant trees and so on. So that's what's going on today.
Just look at this view.
Sorry.
Many years ago, North Dakota looked quite different. Let's go back about
So this is North Dakota.
Years. Back then, the climate in the area we call home was something similar to the climate of Florida. Humid swamps,
in North Dakota,
green plants and lush trees. If it wasn't for that climate, we wouldn't have the coal we use for electricity today. Who knew it took 60 million years to make a light switch work? You see, as the
my PChem students do.
They would fall to the ground and become what's called peat. Peat is a mixture of soil and partially decomposed plant material. Over time, that peat would get piled under more plants, mud, and other sediment, which put a lot of pressure on it. This heated things up big time. The perfect recipe for coal. It's easy. Pressure plus heat plus time equals coal. So what exactly is coal? Well, coal is actually a type of rock. It's dark brown or black, combustible, and formed over millions of years through plant decomposition. There are four main types: lignite, bituminous, and anthracite.
I mean, isn't it strange too? Like some of these rocks that we could dig out of the ground, you could just light on fire. I mean, it's just really, really weird, to think about. And so you might think, well, there's some conspiracy, right, for fossil fuels. There doesn't have to be a conspiracy. It doesn't get any easier than digging up a rock and lighting it on fire. Right? Now, there may be economic, machinations, but the point is, it's so easy. Dig it out of the ground, pulverize it, and you've got energy. Yeah. It's hard to compete against that.
Different from each other depending on how old they are and how long that peat was compacted, pressurized, and heated up. Lignite is the youngest type of coal, and the kind we mine here in North Dakota. For every 10 feet of plant material, 1 foot of lignite coal was created.
That's interesting.
While it has the lowest carbon content, meaning it burns more quickly than other types of coal, lignite is the closest to the ground's surface. Fun fact. Early coal miners used simple tools to dig the lignite out of the ground. It's that close. So how exactly do they turn million-year-old coal into electricity? Well, it starts by getting it out of the ground. There are 5 mines in North Dakota that do this: Freedom, Falkirk, Coyote Creek, Center, and Beulah. Together, these mines dig up millions of tons of lignite coal every year. In order to mine lignite, certain requirements should be met. Ideally, the combined thickness of lignite needs to be at least 10 feet thick in 1 or more different beds. Second, the lignite should be no deeper than 175 feet beneath the surface. And third, there needs to be no more than 10 feet of overburden for every foot of coal. Overburden is a layer of clay between the dirt and the coal. A process called core sampling, where miners drill and remove a cylinder-shaped sample of the ground below, can show if these requirements are met. To start the mining process, lignite companies need to obtain the rights to mine the land from the people who own it, and then permission from the North Dakota Public Service Commission. Part of that permission is a bond that lignite mining companies put money into for the land they plan to mine.
And that's what I was talking about.
This bond is to ensure that no matter what happens, there will be the money available to reclaim the mined land back to a condition.
It can't just be a promise, right? Because what if the company goes bankrupt, which could happen, right? So that money is really there, so it can pay for the reclamation no matter what happens to the company. So that's
good as or better than what it was pre-mining. The whole process helps to ensure and maintain the excellent relationship lignite companies have developed with local farmers and landowners. Once miners have a right to mine, exploration drilling begins. This shows the quality of the coal as well as the amount of overburden that needs to be removed to get to it. The soils and wildlife are examined and any historical or archaeological sites are studied and avoided. Once that's all done, the digging begins. First, to be removed and saved for later are the layers of dirt on top of the overburden and lignite.
So they save the topsoil.
The topsoil and subsoil. For this job, mining companies bring in tractor scrapers, shovels, backhoes and loaders, machines tailor-made to do some serious digging. Fun fact, soil monuments like this one are created to help mining companies keep track of just how much soil has been removed and needs to be replaced after mining. Once the top layers of soil are removed, we reach the overburden. This layer is a bit heavier and denser than the soils above it, so mining companies need heavy-duty machines to get this work done. Sometimes miners run into layers of rock. Want to know how they can do that?
Yeah.
For the rest of the overburden removal.
So there was one of those drag lines in Rockdale. I don't know if you ever drive on Highway 77, going between, say, Giddings and Waco or Cameron. On the left, you could see this big, huge crane. It was bigger than any crane I'd ever seen. Like, what is that? Well, it was a drag line. You can reach out with this big bucket and drag that topsoil and the overburden off of the coal deposit. The big seam of coal right there through the middle of Texas.
Miners bring in the drag line. Let's give you an idea of just how big drag lines are. If you've ever taken a ride on a school bus, that school bus could fit into a drag line's bucket. Now that's a wild ride.
It's big.
Drag lines scoop up the overburden, pile it nearby, and replace it after the coal is removed. Fun fact, North Dakota lignite doesn't have to travel far because power plants were built at the mouth of the mine. This cuts down on the transportation cost of the fuel, since North Dakota lignite is about 1/3 water. Once the drag lines expose the coal, rippers come in to break up the coal, making it easier to remove with haul trucks. Electric loading shovels, hydraulic excavators, and front-end loaders are also used. A lot of machines, each with a very specific job to do. After the coal is removed from the ground, it's cleaned, crushed, and delivered to power plants to be turned into electricity. Even though lignite is close to the surface, making it fairly easy to reach.
I'm breaking this up because it's going to be on YouTube. But the thing about the crushed, you might have heard of this term clean coal in the past 5 or 6 years. And then it's controversial because people say there's no such thing as clean coal, so there's sort of a political back and forth. But what they do is they just changed how much they pulverize the coal. So the combustion efficiency is all about surface area. Okay, so if they make more surface area by making smaller particles, then it burns more efficiently and more completely. And so then they also bubble the air underneath the coal. So they have the powder get dumped into a room, and then the air jets, kind of like a air hockey table. The floor is all full of air jets, and the air percolates through the coal and makes what's called a fluidized bed. So it's not just a pile of coal burning from the top. The air is coming all up through it, and it's just making like a big cloud of coal and air. Really good mixing, and then it burns really efficiently. So that's what they've been able with modern technology, and that's what they call clean coal. Is that with modern technology they pulverize it more and they mix the air better so that you get a better burn.
Mining companies wanted to also preserve the beautiful land we have.
Okay, now we get to the reclamation part.
This is made possible through a process called reclamation, when mining companies return the land to how it was before it was mined. Mining for lignite gained popularity in the early 1900s, but it wasn't until the 1970s that laws were created to protect the lands that were mined. Since then, laws have required.
So that was a coal mine right there.
Return to their original state of productivity, meaning they have to be as good as or better than they were before mining. Reclamation starts by spreading the soil back on the land. In fact, miners replace the soil shaped in the same way it was before mining, restoring wetlands, hills, and valleys. This is called the land's approximate original contour. Seeds of local grasses or crops are planted, and any wildlife habitats that existed in that area are also returned. Once that's completed, the land is monitored for at least 10 years to make sure it's as healthy and productive as it always was. If the land is to be farm or cropland, whoever farmed the land before mining will farm the land during the reclamation process. The growth of the grasses or crops is examined, and the wildlife habitats are closely monitored to ensure that they're thriving. This all must happen before mining companies can be released from their responsibility to the land. Once the Public Service Commission gives the okay, the coal mines are released from bond, and the land can continue to be used for agriculture or recreation. Reclamation is really important to miners in North Dakota. In fact, North Dakota's lignite industry is a leader in the nation in protecting the environment before, during, and after mining. In some cases, land is transformed for newer and better purposes because of mining.
So that's just showing a lake that they have now for recreation. I don't want to run out of time, so I want to move forward a little bit. So the reclamation process was the new thing I wanted you guys to know about. It's not that new since the 70s. I wanted to look at this solar park too, because if we're looking at this compared to the coal-fired power plant, which of these is more resistant to storm damage? We just had a heck of a storm come through. And did y'all see this news article about the solar park that was damaged by hail? Yeah. So this was out of Houston.
The video posted on social media claims that hailstorm damaged thousands of solar panels on a farm in Brazoria County.
One viewer is questioning if this video is real. They show you have verified. Finds out. Thousands of people are commenting on the video that shows lots of damaged solar panels. The post made on X claims this is a result of that hailstorm in Damien, Texas on March 24th of this year. The KHU11 Verify team went directly to our sources to find out if this video that's been viewed more than 4 million times is the real deal. Our sources: the person that made the post on X, Fort Thompson, the National Weather Service, and Ryan Ashcraft of Ashcraft Aviation. We cross-checked the post's claims of a hailstorm on March 24th. Right away, it raised a red flag since the National Weather Service damage reports do not show any hail fell in Dayton, Texas, or in the Houston area that day. You have to go back a little further when the weather got bad in the Houston area on March 15th.
That size piece of ice falling from the sky, people have been seriously injured by hail.
The storm produced hail stretching from West Texas through the hill country all the way to our area. KG 11 viewers in Meadville showing us how big the hail got. NWS reports the largest was the size of a baseball at 2.5 inches. Just about 11 miles from Meadville is Dana, where the video claims to have been shot. An NWS report confirms ping pong ball sized hail fell. So how does the KG11 Verify team know this video is real?
Oh my God.
We tracked down the pilot that shot it. Ryan Ashcraft of Ashcraft Aviation in Bay City shared with us video of his reaction when he first witnessed the damage left by the hailstones. We can verify this video
all busted
real.
up.
It was also shot a week after the storm.
And then you've got, so again, we love to have sort of this positive attitude, right? But you do need to think about what happens when a hailstorm comes through. What happens when, the wind doesn't blow and you've got a windmill and so on. So we're still in this this age of innovation. It's exciting, especially with photovoltaics, but we got to also think about what happens when they get dirty, what happens when the hailstorm comes, and so on. And so I think distributed power in terms of solar makes more sense than localized, right? Because if you have all your solar cells in one localized thing, because you're trying to replace a power plant, so you're still thinking we need a specifically centrally located power source, a solar farm. You're just putting all your eggs in one basket that a storm could come through and destroy. If you have solar panels on everybody's homes, that's distributed power. And that makes a lot more sense because, a hailstorm could come through, but it's only going to take out a few houses. It's not going to threaten the whole grid. So this is our National Renewable Energy Laboratory, and you can go on there to this PV watts, and you can actually calculate the economic impact that would have on your bottom line if you put solar panels on your house. And so that's pretty cool. You can go in. I put in the Houston area. It tells us how much solar light is hitting our house on an average month and what the value is. So I could, annually, it's like $580 of value over and above, what I would typically generate. Now for the homework, did y'all do some of those on, not this week's obviously, but not last week's homework? Was there some solar panel stuff? And this is just the rules of thumb that you should use for those conversions. But things have gotten better. This is $8 a watt. This was what I did years ago when I made those homeworks. Guess what it is now? $1.50 a watt. So we're definitely getting better. And now it's gone up a little bit to $2.50 a watt. But that's fantastic. That's for installed solar. So it's on your house, and that's what it costs. Okay, but still, for your house, your whole house, it would be between $14,000 to $20,000. So it's not cheap, but it's at least within range. It used to be $150,000, then it was $50,000. Now it's getting down into the $20,000. And so it's just starting to get in the range that homeowners are starting to make those decisions and say, I think I want solar panels. They're starting to integrate them with roofing materials. And so they're trying to make roofing materials that are also solar panels. And so then you combine both. So anyway, lots of excitement in the future. And then here's just some other things in the notes. This is the thermal or forever battery. That's plutonium. It's going to generate heat for 24,000 years. Only half of it's gone. So, 240,000 years, it's going to generate heat. And if you have a thermocouple on there, you've got a battery that lasts for 250,000 years. So that's what we put on satellites. And that's fantastic. So, and then lightning. We've still not figured out a way to capture lightning. But you saw from the storm last night, there's a lot of it out there. So we could figure out a way to capture lightning. Whenever they say with current technology, just smile. Because we never stay at current technology.